Hello, this is Sean Leonard, and I'm presenting with Chance Scripter, and I'm presenting on our project for ME404 Sustainability, Approaches to Improved Cooling of Data Centers and Utilizing Waste Heat. Now, the three approaches we're going to cover are environmental approaches, and this is location-based, meaning that it's based on the environment of that location, or the climate of that location, how warm or hot it is, also how humid it is. Source optimization, or source approaches, which is going to be optimizing thermal systems in existing data centers, and also waste heat utilization. So how can we utilize the excess heat created in a data center to either generate energy or just use it as heat? And also performance approaches, which is going to be improvement and optimization of computers themselves to either consume less energy or to generate less heat. Now, inside of current systems, inside of data centers, we use what's called computer room air conditioning, or in this case, it's usually referred to as CRAC, or abbreviated as CRAC. And this is the same as air conditioning used for people, except that it's used to cool computers. Now, in modern data centers, between 40 and 50% of total energy used is just for cooling. And this heat is generally rejected as a total loss, which means that it's taken out to the environment and completely wasted. It never goes anywhere. Now, the drawbacks of CRAC cooling is that the heat's not transferred very well, and I'll explain the reason why here in my diagram. You can see what's here is called a compressor vapor refrigeration cycle, and that's what CRAC's used to cool with. And what happens is a compressor compresses vapor and pushes it through a condenser, which condenses it down to a liquid. This liquid is blown through an expansion valve, and it comes out as liquid and vapor, and then this vapor is put through an evaporator that takes the remaining liquid and evaporates it, and when it evaporates, it takes energy with it. Now, inside the data center, the warm air is going to be coming off the server racks, and that warm air gets blown over the evaporator and cooled, and then it gets looped back into the data center to cool the servers, and so on, so it operates in a loop. Now, the condenser would be placed outside to reject heat to the outside. Now, there's some drawbacks to this. Air has a really low heat capacity. It's something on the order of 1/4 that of water. And there's usually really poor optimization. There's either poor airflow optimization, so air is being allowed to mix, warm and cold air, or it's not flowing very nicely, or there's a lot of obstructions, or they just have no use of optimization at all. They just blow cold air in one end of the room and take hot air out of the other and hope that it works. And this is actually really common in data centers. So I talked about the three different approaches, and so our first approach to try to improve data centers from a sustainability standpoint is an environmental approach. And this is what's usually referred to as free cooling. Now, free cooling doesn't mean that it doesn't cost anything. It means that you're using the environment to get rid of your excess heat. And essentially they call it free cooling because it's released out into the environment. Now, one of the best ways to do this, and especially one of the most sustainable, is direct airside cooling. And as you can see in my diagram here on the right side, this is where you take direct air directly from outside, plummet through your building, through your server racks, and straight back out. Now, this requires no heat exchangers, and therefore is actually really efficient. You don't have that inefficiency of heat exchangers. However, you can only locate this somewhere where the climate is very suitable, in this case not very humid, and doesn't have a lot of pollutants. And because that's not very common in many places, usually what's used is filtered air. And the filtered air comes through a filter, through these louvers, through the server rack, and then it gets exhausted out. Now, this isn't quite as dependent on having fresh, clean air, but it does require cool air. Now, there's also such thing as indirect airside cooling, and this is where you use a heat exchanger. And in this case, this heat exchanger would be located right here, where this fresh air comes in. But instead of the fresh air coming directly in, it would go in through the heat exchanger and back out of the heat exchanger, and then air inside the server room would rotate in a loop. This way, you have two separate air systems, and they don't cross over, so you can control the air on the inside, the pollution, the temperature, etc. However, because a heat exchanger is used, and because heat exchangers are not 100% efficient, you have to have a really large temperature gradient between your fresh, cool air from your environment and your air inside of your server room. And since that's hard to achieve, especially year-round in a lot of places, it's not very common. And unfortunately, while it is very sustainable, it's very difficult to implement. But it can be used as a hybrid in what's referred to as an economizer, and I'll talk about economizers later. Now, another environmental approach, essentially utilizing the same system, but rather with water, is direct and indirect waterside cooling. In this case, this is an example of indirect waterside cooling, and it's a little bit more adaptable. And as I said, water has a much higher heat capacity. But in this case, you're using water to cool the air off, and then you have a cooler outside. This still relies on having very cold air, but you don't have to deal with anything like pollutants and contaminants like you do with direct air. And then the air is circulated inside the room, and this can also be used as a hybrid, and I'll talk more about that. Now, there's some kind of novel approaches to doing environmental cooling of data centers, and one of the cool ones is called Kyoto, or a heat wheel. And this is a rotating heat exchanger, and cold air rotates on the inside of this wheel, and hot air rotates on the outside. And these are actually implemented in a good number of data centers. And the reason they're cool is because they don't take a lot of energy, but you can transfer quite a great deal of heat. And these wheels are quite large. They're often about 12 feet in diameter. Here's a picture of one that was in a data center magazine, and it kind of gives you the idea of how it operates. Now, another version is total loss seawater cooling. And these are very interesting is because the data centers, you can see on the right side here, are mounted on a ship. And what you use as your heat dump is actually the ocean. You use the ocean. And while you are heating the ocean water up, the ocean has almost unlimited heat capacity because of how big it is, so you're not really heating it up. And so you have a very constant temperature coming in from the ocean, and it's kind of a unique concept, but it's actually being implemented in a few places, especially like small islands. It says you can just use the ocean to get rid of all your heat, and it's very inexpensive and it's very sustainable. Now, another way we can deal with our problem of heat generation is source approaches. And our source approach is trying to optimize the current systems to be more efficient and therefore more sustainable. Now, another great way to do this is to use systems as economizers. And economizers are a system that isn't enough to remove all of the heat that you want to, but it is enough to improve the efficiency. In this case, like I was talking about air-based systems or environmental approaches, you can often use them to remove a good chunk of your heat, and that's enough to actually have a very sizable increase in your efficiency, and therefore make it more economic, hence the term economizers. Now, these are actually really useful. And one of the other best source approaches you can use is utilizing waste heat, in this case to generate electricity or work, or you can take that heat and put it somewhere else where it's useful, like heating a building. One of the simplest source approaches is just optimizing airflow. You can optimize airflow inside a building. If you can see on the left side here, we have this cold air coming down through here in what's called an aisle, and you have hot air coming back up and going into a cooler. These are the coolers here mounted on the roof. Now, what they use is called hot and cold aisles, and this is actually utilizing a thermosiphon. So cold air draws down to the floor, goes through the server rack, gets warmed up, and then it wants to rise back up to the ceiling. And in this way, you don't have any pumping losses from moving the air around. So that's an easy way to implement a source approach that optimizes your airflow inside of a data center. Another great example is a thermosiphon cooling. It's very similar to the C-rack systems, except it doesn't use a compressor or an expansion valve. The fluid simply moves on its own. It evaporates, moves up, condenses, moves down, taking heat with it in the process. And these don't require any mechanical input, so they're actually very efficient. Now, a good way to utilize waste heat is using what's called a thermocouple. And thermocouples operate on the Seebeck effect, or a Peltier effect, and they're often referred to as TEGs, which is thermoelectric generators. And they generate electricity directly from heat. Heat moving through the thermocouple generates electricity. Now, they're really useful because they don't have any moving parts at all. And so there's no maintenance, and there's essentially no danger to them, and they're not toxic in any way. However, unfortunately, they have pretty poor heat transfer, so they can't be used directly to cool chips. They have to be used as like an intermediary. But they're still useful, and they still provide a possibility of generating some electricity to increase the sustainability of the heat generated, and that electricity can then be used for other tasks around the data center. Now, another way we can convert heat into some sort of useful energy, we can convert it into work, and we can do that using a Stirling engine. And a Stirling engine is a heat engine that uses the expansion of a working fluid, in this case usually air or refrigerant, to try to push a piston. Now, a hot side is where the heat goes in and it expands, pushing this piston down, and the cold side is where fluid contracts and pulls this piston up. Now, it can provide mechanical work, and this mechanical work can be used to either generate electricity with, or you can use it to run a fan or something similar within your data center. But they have to be remotely located because these take up space. You can't put this inside your server. It has to be put somewhere else. So you'd have to plumb heat to that, and it also takes energy to do that. And for that reason, they're not very efficient. However, they do provide some use for that excess heat energy, but they also require maintenance, whereas our thermoelectric generators we previously talked about require no maintenance. And that's what really makes the thermocouple a more effective way to utilize this extra heat and try to make this heat more sustainable, rather than just wasting all of it. Now, the third good way to deal with waste heat is utilizing it for district heating and cooling. Waste heat, given that it's already in the form of heat, can be used to heat up rooms that need heating. So you can use it to heat up rooms that people are in or other things like that. And it works really well on large campuses. So it works very good for university campuses or business campuses where this heat can be utilized to generally heat rooms or heat water, things like that. And C-rack systems, or computer room air conditioning that we were talking about, it's very easy to use district heating and combine it with these C-REC systems, because most buildings already use an heating and air conditioning system, and you can combine this waste heat from the district heating and cooling out of your data center into C-REC systems very easily. It requires very little effort. They operate on the same principle. Now, this principle is actually considered at the U of I, and it was proven that it was not enough heat from the data centers to heat rooms. However, it was enough heat to be economically feasible, and that's through using it as an economizer. And what I was previously talking about with economizers is economizers don't provide all the heat that you need, or heat removal that you need, but they provide enough to increase the efficiency, so therefore it's worth it to you. And this was studied by the thermal systems class at U of I, and they figured out that they actually could use their heat center, or the heat produced in their data centers, to try and warm up other rooms. And with that, that is the source sustainability options and the environment sustainability options. And I'd like to take it over to Chance Scripter, who's going to talk about optimization of the computer systems.
Hi, this is Chance Scripter, and I'm going to pick up where Sean left off with the performance approach. The cases that I will discuss involve using artificial intelligence to improve and optimize the current data center systems to consume less energy. And in order to understand how this is done, we must first learn how energy is wasted in these systems. Energy is wasted by means of heat generation, inefficient cooling systems, and systems that are still being run during periods of low loads. For example, a server with all systems on during time with no net traffic. To learn how algorithms are used to optimize energy-consuming processes, first we must learn a little bit about the two major subsections of artificial intelligence, machine learning and deep learning. I will discuss these in greater detail in the next few slides, but what's important to note here is that deep learning is actually a subset of machine learning. So a deep learning algorithm uses machine learning practices. Now, what is machine learning? Machine learning is an artificial intelligence algorithm that learns from given data to solve a problem. The algorithm is able to rewrite itself as it learns from new data, improving on its predictions. The more data that is processed, the more accurate predictions can be, meaning that the algorithm is constantly improving over time. In short, machine learning uses data to learn, predict results, and improve on its own predictions. Deep learning is a form of machine learning used by artificial neural networks to process data. Deep is a technical term referring to the many layers of the network, each providing a different interpretation of the data it receives. This allows for the algorithm to extract raw data from the sensors without need for human interpretation. Now, due to the large number of layers or interpretations, deep learning processes tend to be computationally cumbersome. In short, deep learning uses a network of algorithms to interpret and process data similar to neural connections in the human brain. Traditional simulations of data centers as energy balance systems is effective, but doesn't accurately represent heat flow due to the high complexity of equipment design and no account for the change in data center load. A machine learning algorithm was used to create a power consumption model, allowing researchers to simulate performance under dynamically changing operating conditions. This was proven to be an effective way to optimize data center design, with researchers being able to identify poorly performing system components and large sources of heat generation. Deep learning was also applied to interpret months' worth of data from a server room with a traditional vapor compression refrigeration cooling system. Normally, these cooling systems operate off human input set points. For example, an air conditioning unit is set to output air at a certain temperature, and the unit consumes a certain amount of energy to reach that goal. These set points are found through estimation or trial and error, and are usually far from ideal. The deep learning algorithm was set to interpret months' worth of data from these sensors, and derive optimal set points for the cooling system, resulting in a 15% reduction in cooling costs, which can be significant for large data centers. Deep learning algorithms can also be used to predict future server demand. This is known as demand-side management. Demand-side management can be used not only to prepare cooling systems for high loads, or even turn them off during expected periods of low loads, but can also shift peak periods of demand towards peak periods of renewable energy production through consumer incentives. This reduces consumption of non-renewable energy and reduces the need to store vast amounts of renewable energy. This slide also presents the equation for power utilization effectiveness, where the total power of a data center consumes is divided by the power used by its server equipment itself. As you can imagine, machine learning techniques can also be used to optimize this equation, minimizing energy spent on ancillary functions. Here's a diagram showing how machine learning interprets data from a demand-side management perspective. As you can see, many different forms of input, including demand prediction, can be combined and interpreted by the algorithm. In the case of cooling system optimization, these inputs include data from equipment temperature sensors, load sensors, and server room temperature and humidity sensors. The demand would be the predicted amount of heat required to be removed. These inputs are run through the machine learning algorithms, which output the best possible controls, meaning that yields are maximized and costs are minimized, while staying within the system parameters. This process is iterated, sometimes even thousands of times, before the most optimal solution is derived. In conclusion, we presented many different methods for cooling server rooms, but it is worth noting that no one solution is perfect. Environmental approaches result in cheap, energy-conservative solutions, but can only be done in certain climates, and the heat removed from the server rooms is effectively wasted. Source approaches can be effective at recycling or reusing the excess heat, but can be costly and difficult to implement. Performance approaches were proven effective at producing optimized results. However, machine learning algorithms are complex and computationally cumbersome, requiring a large amount of computational power that could otherwise be used to meet server demands. While each solution has the potential to be effective on its own, a hybrid approach would be most likely to produce an effective, sustainable solution. A scheme must be implemented that combines a variety of approaches to reach a solution that is cost-effective, sustainable, and meets the rapidly changing demand of data centers. On a broader scope, data centers consist of approximately 1% of all energy consumption in the United States. As the demand grows and climate change becomes an ever greater concern, the need for a sustainable solution is becoming more vital.